In today's tutorial, we will have a closer look at an NMR spectrum. It's this part of the NMR spectrum of trimyristin. Trimyristin has this structure. It is the main component of the nutmeg. And what we see here, we have three ester functionalities, all of the same fatty acid, the C14 fatty acid, tetradecanoic acid. And what is the alcohol? It's a triol, it's glycerol here in the center. The main part of the long chains have the signals at higher field than 2 ppm at around 1 to 1.5 ppm. Here is the diagnostic region of the proton NMR, and the first signal we will see here is that signal around 6 hydrogens, looks like a triplet. We have a roof effect here because the coupling partner is at the right hand side, somewhere there at around 1.5 ppm. And where does this signal derive from? Well, it's the CH2 group alpha to the carbonyl, which then is coupling with the neighboring CH2 group and delivering then this triplet type signal. Well, I say triplet type because this ester functionality, and therefore the CH2 group, is not chemical identical with the other two CH2 groups, but the difference in chemical shift is so small that they just seem to give one signal. Let's have a look at the signal we have at lower field. One integral is 1 hydrogen. Well, this is that hydrogen sitting at alpha position of that oxygen, and it has 2 oxygens in beta position, and this is the reason why the signal is at the lowest field. It has the highest chemical shift because of the inductive deshielding of those 3 oxygens. Well, we see overall 1, 2, 3, 4, 5 maxima there. But if we have a closer look, well, there might be even more sitting here. Well, what would we anticipate? We have 1 hydrogen with 4 neighbors. N plus 1 means we would anticipate 5 maxima. But it could be, and this is the case here, that the CH2 groups are not identical. Well, this CH2 group is identical to the other one, but the 2 hydrogens within that methylene group are not chemical equivalent. And we can notice that with this fascinating signal, what we clearly see, these are all at overall 4 hydrogens, 2 here, 2 there, but we have within that signal 2 different chemical shifts. Here is 1 chemical shift, should be located central here, and the other one is there. Well, we have within a methylene group hydrogen A and hydrogen B, and they have different chemical shifts. Why is this the case? This is rather interesting, and let us have a look at this Newman projection. So, how can we understand this Newman projection? We have here that carbon atom in front with two hydrogen substituents and one ester functionality. It should be this one, hydrogen, hydrogen and ester functionality. Behind that carbon is located this carbon, and this carbon has additional substituents, that ester functionality, that hydrogen, and here the CH2 group with an additional ester functionality. So hydrogen, ester functionality, and CH2 group with ester functionality. Well, and what can we learn from that Newman projection? Well, we have these two hydrogens, and whatever conformation we will adopt, they will always have a different chemical environment. If this hydrogen would move to this position, then that hydrogen will get to the position where the other one has been before, but nevertheless the whole setup has changed because that ester functionality would then have moved to this position. So, whatever conformation, those two hydrogens have always a different chemical environment. And this means they are diastereotopic protons with different chemical shift, and we will also notice then the geminal coupling constant. Some of you might remember these diastereotopic protons you usually have if you have somewhere a chiral center in the molecule. This is not the case here, but diastereotopic protons can also arise if we have them in close proximity to a prochiral center. And this is the case here, as I have explained with the Newman projection. So, those two hydrogens have different chemical shifts. Here is one chemical shift located somewhere here and the other one here. Then they are coupling with each other. We have this roof effect here from here and there. Then they have a coupling constant with each other across two bonds. It's usually a rather large coupling constant between 16 and 24 Hertz. And where do we find the coupling constant? Well, it's the distance from this signal to that one, or from here to there. And we will find the same distance from here to this one and from this one to that one. So, each of those two hydrogens have additionally a coupling, a vicinal coupling constant to that hydrogen, but these two vicinal coupling constants, they have different coupling constants, as we can see here. One of those two hydrogens has a coupling constant from here to there and from here to there, and this is somewhat larger than from here to there and from here to there. Okay, so we keep in mind, if we have diastereotopic diastereotopic protons, more complex coupling pattern will usually arise. Thanks for listening.